Hi, hello. My name is Kevin Johan Ha. Today I'll be presenting on CD Nozzle. So first of all, compressible flow plays a key role in high-speed systems like jet engines and rockets. So this project uses computational fluid dynamics to study how gases behave inside a converging nozzle, a device designed to accelerate flow to supersonic speeds. Understanding how pressure, velocity, and density interact in these nozzles is crucial for efficient propulsion design.
So I'll proceed with the objective. So the first objective is to connect fluid kinematics with the behavior of compressible flows within converging and diverging nozzles. The second one is to utilize the differential form of mass, momentum, and energy conservation equation to develop models for compressible flow in these nozzles. So the third one is to employ numerical computation tools to simulate fluid flow, converging, diverging nozzles, and critically assess the physical validity of the outputs. So next is the summary of theoretical background. The convergent, divergent, the level nozzle plays a crucial role in supersonic propulsion by converting pressure and thermal energy into high velocity exhaust to generate thrust. So it consists of three sections, which is a converging section where subsonic flow accelerates, a throat where subsonic conditions occur, and a diverging section where flow becomes supersonic. Flow behavior depends on the pressure ratio between the nozzle inlet and outlet, which affects whether the flow remains subsonic, becomes supersonic, or forms shockwave. Optimum performance is achieved under perfectly expanded conditions where the exit pressure equals ambient pressure. Under expanded or overexpanded flows reduce efficiency. Computational Fluid Dynamics, which is CFD, is used to analyze flow characteristics within the nozzle, with studies like our journal confirming CFD's reliability in simulating compressible flows and supporting theoretical results.
Hi everyone, in this study we review a CFD analysis of the lava nozzle, a convergent and divergent nozzle used to accelerate flow from subsonic to supersonic speed. The paper simulated pressure, temperature, velocity and density changes along the nozzle then using ANSYS Fluent, and even modeled shockwave under different pressure. The nozzle was modeled in 2D with specific dimension like 210 ml throat diameter and divergent angle of 54.5 degrees. What made this paper stand out was it was a clear explanation of isentropic flow, Mach number behavior and shockwave dynamics, all backed by theoretical and simulation comparison. However, it lacked discussion on result discrepancy and didn't cover turbulence modeling or design optimization. Still, the detailed CFD workflow makes it a strong benchmark reference for our project.
Hello everyone, in this video, I will walk you through our CFD simulation process for a converging-diverging nozzle design. This involves key stages which are geometry modeling, meshing, boundary setup, solver settings and result interpretation using ANSYS Fluent. First, we design the nozzle using Design Modeler. The geometry includes a converging section, a narrow throat and a diverging section to facilitate compressible flow acceleration. The design follows reference dimensions from a day-level nozzle journal for validation purposes. Next, we applied a quad-dominant meshing strategy. Face meshing, face sizing and edge sizing were carefully selected to define the grid near the throat, where changes in flow properties are most intense. This ensures more accurate simulation results, especially for high gradients like shockwaves. Beyond that, the inlet, outlet, wall and symmetry were labeled using the name selection feature to be detected by ANSYS Fluent. Subsequent step will be the pre-processing method. Standard air properties with ideal gas behavior was used as flow medium. Let's have an overview of all general inlet and outlet conditions. These settings enabled analysis of the subsonic to supersonic transition. The simulation was initialized from the inlet using default reference values. We assigned 1500 iterations with a tuned Coulomb number of 5 to ensure stable convergence. This plot represents the scaled residuals for key flow variables which are monitored throughout the simulation. Inspected variables include continuity, velocity components, energy and turbulence parameters, which comprises of K and omega value.
Hello, my name is Nurul Atira binti Muhammad Zaki with metric numbers 212648. Now, I will present the methodology we follow for our project. So the first step was conducting an in-depth literal review. We gathered several nozzle-related journal articles that align with our study course. The focus was to understand how velocity, pressure, density, temperature, and Mach number change across converging diverging geometries. This helped us define the physical phenomena we needed to replicate and analyze in our simulation. Next, we move on to designing the nozzle geometry in both 2D and 3D. The initial design parameters were adapted from the reference journal to ensure accuracy and relevance. We also made modifications such as changing the throat diameter and converging angle to study the effect of these variables when compared to standard configurations. With the models ready, we perform CFD simulation using ANSYS Fluent. We simulate compressible flow through both our new design and the journal-based design. Special attention was given to mass generation and streamline observation. To better understand flow characteristic, we analyzed contour plots showing the difference between inlets and outlets conditions. In this phase, we evaluate the numerical data collected from the simulation. We focus on identifying critical regions such as areas of shock wave, flow separation, or high Mach transitions. These changes were interpreted to understand their impact on the overall fluid dynamics behavior of the nozzle. Based on our findings, we conclude that boundary conditions play a crucial role in nozzle efficiency. We documented how different boundary setups influence simulation results. We also reported the average number of iterations and discussed the initializations methods used for convergence. To present our findings effectively, we create a video presentation. This includes a well-structured script, a visual integration of CFD outputs, solver settings, and post-processing results. The goal was to make the simulation outcomes easy to understand for viewers. Finally, we ensure our report and video meet all assignment requirements. Both were prepared according to the given submission guidelines.
For CFD result and analysis, so this is the result that our group get. For first is velocity variation, which is a velocity velocity increase from inlet to outlet, which is at the inlet the minimum velocity we get 36.7 meter per second, and at the outlet it increased to 586.7 meter per second. So as you can see in the picture, the red areas on the contour is indicate high velocity. Remember, for the blue areas show this lower inlet flow. So for this our result compared to journal, our velocity percentage is higher than journal, which is our result we got 5%, and then the journal we got 5 to 5.6 meter per second. So this our nozzle designs to show the flow accelerate in the converging section, which is the sonic speeds at the top, and become supersonic in the diverging section. For our pressure variation result, at the contour plot for the graph, at inlet we got the maximum value, which is 1.17, and at the outlet we got the minimum value, which is 5.08. So this we show the decrease follow Bernoulli principle, where the pressure reduced as a velocity increase in the expanding section. So if you can see at the picture, the red at the inlet is high pressure, and where the blue color at the outlet is the low pressure. So our maximum pressure is 31% lower than journal, which is the 1.71 PA. So due to lower inlet pressure or lack of a decay shock wave model, that's why we got our maximum pressure is 31%. For the temperature variation result, at the inlet we got 299.3 K. Remember at the outlet we got 277.8 K. So this is show the transition from the red area to blue in the contour, which is the cooling efficient. So this result we show the gas expansion in an adiabatic process, which is converting thermal energy into kinetic energy. So for density variation result, as you can see for the picture, so the graph the decrease from 40.8 kg meter per cube at the inlet to 1.786 kg per meter per cube the outlet. So this consistent with the other gas, which is as the pressure drops and the temperature slightly raises. So for the picture, you can see the contour shows the red color at the denser inlet and the blue area at the less dense outlet. So this shows that our density is lower, which is 29%, than the journal, which is 20.8 kg meter per cube. And the last is mesh number variation. So the mesh number confirms supersonic flow, which is rising from 6.52 at the inlet to 2.11 at the outlet. So this increase is visible as the red in the diverging section, related the nozzle's ability to transition from subsonic to supersonic speeds. So as you can see from the graph also, the higher mesh number is critical for propulsion application. So the exact value may reflect simulation assumptions. So this is the result, our shock wave result, which now we have a 5 shock wave result, which is velocity variation, pressure, temperature, density, and mesh number. So as you can see, velocity dropped to 68.1 meter per second, which the error is 364% from theoretical, which is 456 meter per second. So for the pressure show 12.5% error, which is the phase is between 152, 106 versus 171, 106 PA. So for the temperature, show the 29.07% error, which is the value around temperature is 227 K versus 263 K. So for the density, we got error 43.5% error, which we got 36.5 versus 20.62. So this difference indicate the shock was not well captured, possibly due to the courses machine or early shock formation. So this is the shock wave that we got, our group got for the final compared to the journal result for shock wave.
So in conclusion, the CFD simulation confirmed the expected compressible flow behavior in a CD nozzle. Velocity rose from 36.7 to 586.7 meter per second, with pressure dropping from 1.17 megapascal to 40.8 kilopascal, and temperature from 209 to 277 Kelvin. The Mach number also exceeded 2.11, verifying the supersonic flow. So this result matched theory very well and proving the CFD value in analyzing and optimizing high-speed nozzle design.